Section 7.10, octahedral complexes. We'll talk about their geometric isomers. Ma6. All 6 ligands are exactly the same. There's only one way of arranging these 6 identical ligands. What if we replace 1A with a B? You can put B on top, bottom, left, right, front, and back. But still, these 6 structures are identical to each other. There's no difference. They are superimposable on each other. Now, what if you have 2 Bs and 4 As? So these 2 B ligands are different from those A ligands. In this case, we can have cis versus trans. So if you put these 2 Bs on just the same side of M with an angle of 90 degrees, this is cis. Or you can put these 2 Bs on the opposite sides with respect to the transition metal center with an angle of 180 degrees. This is called trans. Now, what if you have 3 ligand A's and 3 ligand B's? A and B are different, and then we have 2 different geometric isomers. Facial, Meridiano. The shorthand notation for facial is FAC, F-A-C. The shorthand notation for Meridiano is MER, M-E-R. Let's look at the pictures first. This is Meridiano. You may notice that these 3 A's are on the same plane with 3 different angles, 90, 90, and then 180. 180 is different from 90 and 90, so there's 180 here. And also, simultaneously, the 3 B's will have to occupy a plane that's perpendicular to the plane of A's. And this is Meridiano. This is facial, and now if you look at the 3 A's, the angles are 90, 90, 90. All 3 angles are exactly the same. They're 90 degrees. Well, what if these 3 B's are replaced with 3 different ligands? Let's say C, D, E ligands, 3 different ligands. Still, we call this facial. So, and then this is going to be Ma3 DEF, something like that, or CDE, something like that. So, as long as you have 3 A's and their angles are all 90 degrees, it's facial. And over here, if you have 3 A's with angles being 90, 90, and 180, that's Meridiano. What if you have 3 different kinds of ligands, A, B, and C, and you have 2 A's, 2 B's, and 2 C's, and then we have 6 geometric isomers. We have trans, trans, trans in the order of A, B, C. That means the 2 A's are on the opposite sides. The 2 B's are also trans. The 2 C's are also trans. And then we can have just 1 pair of identical ligands on the trans position. So in here, that means the 2 A's are trans. They are on the opposite sides to the metal. And then the 2 B's are cis. Well, and then of course the 2 C's will have to be cis. Remember again, if you just picture this, the 2 A's are on the trans positions, and then you imagine the 2 A's are on top and bottom of this transition metal, and then you have 2 B's and 2 C's on the same plane as the transition metal, and then they have to either be both trans or both cis. You can't have 2 B's are trans and then 2 C's are cis. That's impossible. So, but now here you can have arrange the 2 B's to be on the opposite sides, and then the 2 A's will have to be cis. The 2 C's will have to be cis. Of course, they can both to be trans, but we talked about that. We included that situation, that scenario here. All right, over here, the 2 C's can be trans, and then the 2 A's and the 2 B's are both cis. Of course, you can have cis, cis, cis. So the 2 A's are cis, the 2 B's are cis, and the 2 C's are cis. In this case, there are actually 2 enantiomers. This transition metal complex structure is chiral. This is because this structure lacks improper rotation symmetry element. So what's improper rotation symmetry element? That means you rotate this structure a certain number of degrees. So if it's Sn improper symmetry element, that means you need to rotate this structure 360 divided by n degrees, and then followed by a reflection with respect to a plane, symmetry plane, perpendicular to the rotation axis. So let me give you an example. S1. S1 means you rotate the structure 360 degrees, followed by a reflection. So S1 is simply just a symmetry plane. What about S2? S2 means you rotate this structure 180 degrees about an axis, and then you do a reflection with respect to a symmetry plane that's perpendicular to that axis. So in that case, S2 is equivalent to the center of symmetry. Why is that? This is because when you, let's say we rotate the structure about the z-axis 180 degrees, and that's equivalent to changing the coordinates x and y to negative x and negative y. And then you do a reflection. That will change the z coordinate to negative z. So overall, S2 symmetry operation will change the coordinates x, y, z to negative x, negative y, and negative z. Now it's clear that S2 is equivalent to the symmetry operation regarding the center of symmetry. So again, in total, there are 6 geometric isomers. They can be A trans, B trans, C trans, A trans, B cis, C cis, A cis, B trans, C cis, A cis, B cis, C trans, and A cis, B cis, C cis. In this scenario, there are 2 different enantiomers. They are mirror images to each other. They are non-superimposable on each other. Now let's look at the mirror images. So cis A, cis B, cis C, cis C, cis B, cis A. And now you can see they are mirror images to each other. And also, if you just look at this structure, it does not have a S1 symmetry element. So again, S1 is just symmetry plane. There's no symmetry plane here. All right, there's no symmetry plane here. And then there's no center of symmetry. That means there's no S2. Okay, there's no S1, there's no S2, and then there's no S3. I mean, we can't even find a C3 rotational axis followed by a reflection. I mean, it's just you can't find it. Usually, if you have a S3 symmetry element, we should be looking at 6 or 3 or integer multiple of 3 identical ligands, but we don't have that. And of course, there's no S4, there's no S5, there's no S6. So this structure lacks any improper rotation axis. All right, so that means, well, this one is chiral. We can find its mirror image, and these 2 mirror images cannot be superimposed on each other. Now again, 3 different types of ligands, and then let's say we have A3, B2, and 1C. Once you have 3 identical ligands in the octahedral complex, you'll see we can just look at the positions of these 3 identical ligands and say whether it's facial or meridiano. And then you have 2 Bs. When you have 2 Bs, well, it's possible to have this 2 Bs on the same side, that's cis, with a B and B angle of 90 degrees, or it can be trans with a B and B angle of 180 degrees. So in that case, we have 3 different isomers. It can be facial, referring to A. So over here, I want to show you the facial. So this is facial, 90, 90, 90. So all AMA angles are 90 degrees. And in that case, the two B's will have to be cis. There's no way for the two B's to be trans, and then therefore we do not have to specify cis or trans for the two B ligands. So look at this, cis. And if I move this to here, it's still cis, right? If I move this to here, it's still cis. It has to be cis. Once the three A's occupy the facial positions, the two B's will have to be cis. Now, the three A's can be in meridional positions, AAA, 90, 90, and then don't forget this, 180 degrees, 180 degrees here. And then in this case, the two B's may be trans or cis. So that's why you have three different kind of geometric isomers when you have three A's, two B's, and one C. Over here, you're looking at facial, meridional, referring to the three A's, trans referring to the two B's, and over here it's meridional, cis. Meridional is referring to the three A's, and cis are referring to the two B ligands. Don't worry about the position of the C ligand. What if you have four different kind of ligands? Let's say it's A2, B2, C, and D. And of course you can have A3, B, C, D, but that's going to be easy. If you have A3 and then B, C, D, well, it's going to be either facial or meridional, right? It's going to be facial or meridional regarding the three A ligands. When it's a meridional geometric isomer, I'm talking about A3, B, C, D. And then the three A's are on the same plane, and the same plane contains the transition metal. And then you can tell the transition metal and BCD are on the same plane, so there's one symmetry plane there. This meridional MA3BCD has a S1 improper rotation symmetry element. It's A chiral. I'll let you think about the facial MA3BCD and see if you can find any improper rotation symmetry element. And let's get back to this. Okay, I just talked about A3BCD, but now let's talk about A2 B2CD. This one has 8 geometric isomers. So how do we count the number of geometric isomers properly for such a complex structure? Well, first, you can just look at the C and D, and you can put this 2 on the transposition. And then MA2B2 will be on the same plane. So let's say you put C on top, D on the bottom. Okay? And then MA2B2 will have to be on the same plane in the middle. And the two A's can be trans. The two A's can be cis. All right? And then when these two A's are trans, the two B's will have to be trans. When the two A's are cis, the two B's will have to be cis. All right? So we have this kind of scenarios that include only 2 isomers. Are there any enantiomers? No. This is because when you put C and D on the opposite sides, and then you can imagine there's a symmetry plane that contains C, D, and the transition metal, and then it should either contain the two A's or bisect the two A's. Now, what if CD are cis? Well, this is really complicated. When CD are cis, there are 6 additional isomers. So when CD are cis, you can have AA trans, you can have BB trans. So I want to show you this. When CD are cis, let's say we put CD, the two B's and the metal on the same plane in the middle, and then one A on top, one A on the bottom. So in this case, you have AA in the trans position, BB in the cis position. Or you can put BB in the trans position, and then AA will have to be in the cis position. So you have 2 isomers here. Right, again, over here we're talking about 2 geometric isomers. And then there are 4 more different geometric isomers. So we can have both AA and BB to be cis. So AA cis, BB cis, AA cis, BB cis, AA cis, BB cis, AA cis, BB cis. And in this 4 isomers, these 4 are different. Okay, now let's look at the difference. In these 2 geometric isomers, A and D are on the opposite sides. In this 2, B and D are on the opposite sides. All right, so A and D, A and D, B and D, B and D. Now, what's the difference between these 2? Well, they are enantiomers. They are mirror images of each other. They cannot be superimposed on each other. Why? Because if you just look at one of these 2 structures, any one, you cannot find the there's no center of symmetry. That's obvious. And actually, there's no symmetry plane either. That means there's no S1, there's no S2. What about S3, S4, S5? Usually you have to have integer multiple of 3 or 5 or 5, 3 or 4 or 5 identical ligands, and we don't have those. So now it's clear that the structure lacks improper rotation symmetry element, and then the structure is chiral. Since it's chiral, we can find its mirror image. It's right here. So C is the mirror image of this C. A's mirror image is right here. 2B is here, 2B is here, and then AADD. So these 2 are a pair of enantiomers. Similarly, these 2 are a pair of enantiomers. Now we have 5 different ligands. This is even more complicated. There are 15 geometric isomers. So first, let's put these 2 A's on the transpositions. And then there are 3 different isomers. You can have B and C on the opposite sides. That's one isomer. B and D on the opposite sides, another isomer. B and E on the opposite sides of the metal. Well, that's the 3rd isomer, so you have 3 isomers. Do they have enantiomers? No. This is because, again, just picture this. You put one A on top, one A on the bottom, and then in the middle there's a plane that contains M, B, C, D, and E. This plane is the symmetry plane. And once you have a symmetry plane, you have this S1, improper rotation symmetry. There's no enantiomers. Thus, in this case, when AA are trans, the structure is achiral. And then what if the 2 A's are cis? Well, and then there are 12 isomers. 12 isomers. Actually, it's 6 pairs of enantiomers when AA are cis. Why is that? Why are there 6 pairs of enantiomers? Well, this is because when the 2 A's are in the cis position, and now imagine you put this 2 A's and 2 other ligands and the transition metal on the same plane, and then you need to put one ligand on top, another ligand on the bottom. So there are 6 different arrangements. Okay, you can put BC, one on the top, one on the bottom. Okay, they are, so it doesn't matter which one is on top, which one is the bottom, because they will be identical. But anyway, you can put one BC, the pair of BC, on top and bottom, BD on top and bottom, BE on top and bottom. You can put CD, one on top, one on bottom, and CE, one on top and one on bottom. So I just enumerated 6 possible arrangements. And for each such arrangement, due to the lack of improper symmetry element, all 6 are chiral. And that means you have 6 times 2 isomers, or 6 pairs of enantiomers. Okay, now what if you have 6 different ligands, A, B, C, D, E, F? They are all different. There are 15 pairs of enantiomers. Why 15? Okay, now let's again look at this. You can have, let's just look at the vertical axis. Okay, you can have AB on top and bottom, a C on top and bottom, a D on top and bottom, a E on top and bottom, a F on top and bottom. So there are 5 different arrangements regarding A and one of the other 5 ligands, right? And then there are 4 ligands left, and we need to put them in the middle plane. Let's say the other 4 are C, D, E, F, and then, well, CD can be trans, CE can be trans, CF can be trans, right? So there are 3 more options. So once you made the decision which ligand should be on the opposite side to A, you have 5 options. It can be B or C or D or E or F on the opposite side to A. So that's 5 options. And then for each of the 5 options, you will have 3 options to arrange the remaining 4 ligands. Again, if the remaining 4 ligands are C, D, E, and F, then C and D can be on transpositions, C and E can be on transpositions, C and F can be on the transpositions. So there are 5 times 3 different options. And 5 times 3, that's 15 options. So that means you can have 15 different arrangements of the 6 ligands. And don't stop there. Don't stop there. So once you have this 15 different arrangements, you'll realize that none of the 15 structures has any improper rotation symmetry element. And that means all 15 are chiral. All 15 will have their enantiomers. So we have a total 15 pairs of enantiomers, or 30 geometric isomers, when all 6 ligands are different from each other. Now let's talk more about chirality. Chirality can be found again in cis A2B2C2. We talked about this. But now, what if we have some bidentate ligands, and that makes things really complicated. So in this case, we have cis Ma2L2. So this cis is referring to this A2. This A2 are on the cis positions. In this case, I'm going to give you a specific example. Cis. This is cobalt. This is chlorido ligand, and this is 1,2-diaminoethane ligands. So this is a dichlorido bis 1,2-diaminoethane cobalt, because this one bears a positive charge. And we need to specify the positions. These 2 chlorido ligands are on the cis position. So they should form a 90 degrees here. They are on the same side instead of the opposite sides. Again, this is 90 degrees between the 2 chlorido ligands. Now let's look at this En. En stands for 1,2-diaminoethane. This is a bidentate ligand. So you have NH2 here, NH2 here. This is the linkage. This is CH2, CH2. So again, this is NH2, CH2, CH2, NH2. All right. So one bidentate ligand, the other bidentate ligand. So if you just focus on just one of those 2 structures, it lacks S1, S2, S3, or S4, etc. It does not have any improper rotation symmetry element. Therefore, the structure is chiral. It has a mirror image, and these 2 mirror images are not superimposable on each other. There's another scenario. We can have 3 bidentate ligands bonded to the same transition metal. In this case, let's look at this example. We're using a different ligand here. ACAC. ACAC stands for acetonato. So the general name is acetonate. I think I have a typo here. Acetonate. So really, it's aceto is CHCO functional group. So you have CHCO functional group, And this is acetonate. This is just the conjugate base of acetone. Okay, so this is the structure of acetonato ligand, CH3CO, and over here, this is CHCOO, CH3. You can put this negative charge on this CH, but also due to the conjugation, you can form a double bond between this carbon and this carbon, and this negative charge will be on this oxygen. And also, it's possible to form a double bond between this carbon, and again, you have this negative charge fall on a oxygen atom. So you can draw three different resonance structures. Okay, three different resonance structures with this negative charge on this carbon, on this oxygen, or on this oxygen. But mostly due to the higher electronegativity of the oxygen atoms, so mostly the negative charge is either on this oxygen or on this oxygen. Therefore, these two oxygen atoms can serve as points of attachment to the transition metal. So it's illustrated here. This is 1 ACAC, second, third, 1, 2, 3. If you look at this structure carefully, it does not have a center of symmetry. All right, and of course, I mean you can say, well, if we do inversion from here to here, I mean if you just look at the red spheres, I mean that's right. But if you look at the linkage here, well, there's no linkage on the opposite side with respect to the center of symmetry. So if you look at this linkage here, there's no linkage on the opposite position. So in that case, we conclude this structure lacks S2, improper symmetry element. And also there's no symmetry plane. I mean, this is there's a linkage here. So if there is a symmetry plane that contains this, just imagine this. This symmetry plane does not bisect this link or this link. All right. So again, there's no symmetry plane. That means there's no S1, improper symmetry element. So over here, this is another way to show you the structure of this kind of transition metal complexes with three identical bidentate ligands. So in this case, well, the point of attachments are just nitrogen, all right? And we label this delta. So really, you kind of have to imagine we're trying to screw. This is a screwdriver on your end. You are holding this. You are trying to screw this so that this triangle and this triangle will be aligned in a ellipsed conformation. So you'll have to kind of rotate it this way. This nitrogen should go here, all right? And this is clockwise. If it's clockwise, it's labeled delta. And over here, you'll have to kind of, again, you'll have to look at this linkage. You'll just have to rotate this to here and rotate this to here, rotate this to here. And this is counterclockwise. It's labeled lambda. Of course, you do not have to always have this N as the point of attachment. You can have O. So En is 1,2-diamino ethane. This is oxalato with two oxygen atoms as the points of attachment. And again, you'll have to rotate this oxygen to here, following this link, and this is clockwise. And this is counterclockwise. Now we have delta and lambda. Enantiomers can rotate the polarization plane of a light at a specified wavelength, not at all wavelengths. And if the enantiomer rotate the polarization plane of a light clockwise, it's called D isomer or plus isomer. If the rotation is anti-clockwise or counterclockwise, it's called L isomer or negative isomer.